this. So, getting on to our review of electromagnetism. So, we're going to be going back over electrostatics. So remember, electrostatics involves charged particles which create an electric field and influence one another due to their charges. The reason that we call these electrostatics is because the charges are staying stationary. Electric, stationary, electrostatics. However, when we get into magnetism, the charges are going to be moving. And because the charges are moving, they're generating a magnetic field. So, when we're talking about electrostatics, we're talking about the force generated by the particles due to their charge. So, to calculate the force on two charges due to their electric field, we need to use Coulomb's law, which is in your formula sheet. It tells us that the force between the two charges is going to be equal to Coulomb's constant, and that number is in your formula sheet as well, multiplied by the two charges themselves in coulombs and divided by the distance between them. So what this tells us is that a greater force is going to be exerted if the charge on the two particles is greater, and the greater force is going to be exerted if the particles themselves are closer to one another. Again, similarly to with Newton's laws and gravity, the force acting on the two objects is going to be equal. Because remember, applying Newton's laws, every action has an equal and opposite reaction. So even if the two particles themselves have different charges, the force exerted on both of them is going to be the same. Okay. The direction of the electrical force is going to depend on the charge. So remember, like charges repel, two positives are going to move away from one another, two negatives are going to move away from one another, but then the opposite charges attract. So, electric field strength is given or measures the intensity of the force experienced by a charged particle in an electric field. And this is going to be given to us by the equation electric field strength is equal to force divided by charge, or in other words, the Coulomb's constant multiplied by the charge and then divided by the distance squared. Okay, now getting on to moving charges, or our magnetic fields. So, as I said before, electrostatics concerns charges which have which exert forces on one another due to their electric fields. But now we're getting on to moving charges. So when a charge moves, it is going to generate a magnetic field. So point charges moving through an electric field have a force exerted on them according to the right-hand motor rule. And this basically just tells us that the force, the magnetic force, the direction of the field, and the velocity of the charge are all going to be perpendicular to one another. So you can just use your fingers. The strength of this force on a moving charge is going to be given by force equals QVB sine theta. Getting onto flux, strength, and production. So, magnetic substances and electromagnetics produce magnetic fields. Remember, magnetic field lines are drawn from positive to negative. So they're drawn from the north to the south. The magnetic flux is the quantity of magnetic field passing through a given area, and the magnetic field strength is the flux per unit area. So a way to think about this is if you have this square area here, and you have 4 magnetic field lines passing through it, the magnetic flux of this area might be 4, right? However, if we consider this to be, or if we wanted to find the magnetic field strength, and this was, say, 4 meters squared, then 1 meter squared per unit area is only going to have a magnetic field strength of 1 Tesla. So the magnetic flux tells us like how many lines pass through any given area at all. You know, you can have an absolutely massive area and have a lot of magnetic flux. However, with that same massive area, you could have a very small magnetic flux density, because even though it's a massive area, you know, the reason that the magnetic flux is so high is because it's a massive area, but when you actually take it per unit area, there's not actually a lot of lines passing through each unit area. And this is, of course, why the magnetic field strength is the flux per unit area. So, the magnetic flux is given by the magnetic field strength multiplied by the area, of course. And then we can determine the direction of the field given current, or vice versa, using the right-hand rule. So this is shown down here. So if you get out your right hand, you can use this to tell you the electric current and the direction of the magnetic field around a current carrying wire and also around a solenoid. So we'll go over the current carrying wire one first. So when you're considering a current carrying wire, of course, the current in the wire is like moving electrons, moving charge, which is going to generate a magnetic field. So when you're considering a current carrying wire, your thumb is going to be pointing in the direction of the conventional current, not the actual current, the conventional current. Remember, conventional current is opposite to the actual current. And a lot of questions are just going to give you the current in terms of conventional current anyway, so don't worry too much about it. It's mostly just when you get into questions involving moving charges, like singular charges rather than current carrying wires. So yeah, your thumb is going to be the current, and then your fingers are going to wrap around and they're going to tell you the direction of the magnetic field. And it's going to act kind of in this circular way. around the wire. Now, getting onto our application of the right-hand rule with solenoids. So, remember, a solenoid is a coil of wire, current carrying wire, wrapped in this kind of, with like this core in the center. And because we have this coil, every single section of this current carrying wire is going to be generating a little magnetic field around it. So this section is going to be like this, like this. It's going to be generating all these little like loops around each section, because that's what we've seen in this example over here. And this all accumulated together is going to generate this combined magnetic field through the center of the solenoid. So when we're using the right-hand rule with solenoids, we need to consider our fingers being the current instead of the magnetic field as they were with the current carrying wire. So our fingers are going to represent the current in the wire, and then our thumb is going to represent the direction of the magnetic field. So our thumb is going to be pointing towards north. So in this example here, our thumb is going to be pointing to the left, because that's the direction of north, and because of that we can tell which of these is the we can tell the direction of the current. So our fingers are going to be wrapping around this way, or like kind of away from you. So this tells us that the conventional current is going to be moving kind of in this direction, which makes absolute sense. Remember, because it's the conventional current, so conventional current moves from the positive to the negative. Of course, you might remember from year 11 when we went over electric circuits that electric current is generated by moving electrons, moving from the negative terminal to the positive terminal. However, that is the actual current. The conventional current is the opposite of that, as I said before. Okay. This is our syllabus link for magnetic fields. So what we need to do, or what we need to learn for magnetic fields, is we need to define a magnetic field. We need to understand representing all of the properties of magnetic fields. We need to solve problems involving magnetic fields and current carrying conductors and wires. So let's get into how we actually do that. So we can determine the magnetic field in a number of scenarios, including the magnetic field on a moving point charge, such as like a moving electron. And this is given by our first equation here. Magnetic field strength is equal to mu naught, which is the permittivity constant, and that is also in your formula sheet, divided by 4 pi, multiplied by Q, which is the charge on the point particle in coulombs, multiplied by the velocity of the charge, multiplied by the radius, the distance from the charge wire or coil, and then divided by r cubed, sorry. The magnetic field strength on a current carrying wire is going to be equal to the mu naught multiplied by the current traveling through the wire divided by 2 pi multiplied by the distance from the wire. So this is going to tell us the strength of the field at a particular point away from the wire, and our particular point is going to be our radius. It's going to tell us how far away we are from the wire. So for solenoids, we need to find the magnetic field strength in the center of a solenoid, we're going to use this formula here. So we're going to have 2 pi times K, our magnetic constant, multiplied by the number of turns multiplied by the current through the solenoid divided by the length of the solenoid. Okay, now we are getting onto forces on wires and parallel conductors. So, a current carrying wire is going to generate a magnetic field, of course. However, when a wire is placed within proximity of another wire and they both carry current, their magnetic fields are going to interact with one another, right? So they both can generate magnetic fields, but they're going to interact. So if you have a look at this example here, we have these two wires. Remember, I'll just write this down now. Excuse me. Our notation for wires or field moving into the page and out of the page is noted by these two symbols. If it's out of the page, it's going to be the dot inside the circle, and if it is into the page, it's going to be the cross. The reason, or a way to remember this, is if you think about an arrow. If an arrow is flying away from you, you're going to see like the crossed kind of feathers at the back. So if an arrow is moving away from you, it's moving into the page because you see the back of it. If an arrow is moving towards you, you're going to see the tip of it, and that's going to be moving out of the page towards you. So that's just how we display if a current carrying wire or a field is going into or out of the page. So as you can see here, our two wires are both carrying current into the page because I have a cross there. So their currents are moving in the same direction. So as you can see, this is going to create this massive loop of a magnetic field. And that's because if we use the right-hand rule, with our thumb going into the page, at all points on either of the wires, the magnetic fields generated are going to combine, right? And because of that, if we have two wires traveling in the same direction, as we have here, or I should say rather with current in the same direction, they're going to be attracted to one another, right? They're going to be pulled closer to one another. However, if we have two wires with current moving in the opposite direction. So for this one here, it's moving into the page, and this one is moving out of the page. If we consider our right-hand rule, so for our first one, it's going to be moving into the page, so our force is going to be moving around in this direction. And for our second one, our current is moving out of the page, it's going to be moving around in this direction. As you can see, the forces are going to cancel out, or rather oppose one another, because at this point, as a result of this wire, the force wants to move in this direction. But the force as a result of the other wire wants to move in this direction. So they're going to kind of oppose one another. And as a result, when we have two wires that have currents moving in opposite directions, they're going to be repelled from one another due to the interaction of their magnetic fields. Okay, now getting on to electromagnetic induction. So, what we need to know for electromagnetic induction is all of the terms listed involving flux, electromotive force and induction, and Faraday's and Lenz's law. And then we need to solve problems involving these terms and laws. So, electromagnetic induction is the production of an electromotive force, causing electrons that are free to move to migrate to one end. As a result of this movement of electrons, a potential difference is going to be caused, or in other words, a voltage. So, as you can see, in this case, the magnet moving is going to produce a force in this coil, which is going to create a current, which we have measured with this galvanometer. So, the strength of the EMF induced depends on the rate of change of flux linkage. For the movement of wire through the field, EMF is given by the magnetic field strength multiplied by the length of the wire multiplied by the velocity that the wire is traveling at. If the wire itself is not perpendicular to the field, then we need to consider the angle at which the wire is at with the field. And this is, of course, because as the wire becomes more and more parallel to the field, it's going to be experiencing less and less of the force. So, if this is our field, and then we'll have our wire. If the wire is perpendicular to the field, then like every single point of that field is going to be like interrupting the wire, right? However, if the wire is kind of at a diagonal, then some of the field or some of the field's components are going to be missed because this wire now has components that are in the same direction as the field, meaning that they're not experiencing anything. Of course, if a wire is just like this and it's parallel with the field, then none of the lines are intercepting with it. So that's why we need to consider this sine theta. What this tells us then is that if a wire is completely parallel to a field, or in other words, if theta is 0, then there's not going to be any force induced. And that's of course because the sine of theta of 0, is equal to 0. So that's just something to remember, mostly for kind of maybe a multiple choice question. So now getting on to Lenz's law. So Lenz's law is kind of, at least what I considered in year 12 to be the most difficult part of electromagnetism. So Lenz's law is an expression of negative feedback. What this means is that the current induced in a conductor by a changing magnetic field is in such a direction that its own induced magnetic field opposes the change that produced it. And this is kind of hard to wrap your head around. So what this basically means is that if you induce a current using a magnetic field, then the current you induce is going to kind of retaliate, and it's going to generate its own magnetic field in a direction that opposes your own magnetic field, right? How I kind of thought about this in year 12, just because it was kind of such a difficult concept for me, I had to think about it a lot, was that the current that I was inducing was like being a little bit petty. You know what I mean? And there is actually a scientific explanation for this, which I'll get into in a second. But how I kind of thought about it was the current was being petty. I was trying to generate this current using my own magnetic field, and then the current that I was generating or inducing was kind of being like, I refuse this. I refuse this magnetic field that you're introducing. It was kind of being petty. Now, the actual reason this happened is obviously not because the current is being petty. It's actually due to the law of conservation of energy. So, I'll explain this in the context of, I don't know what that word was, in the context of the solenoid, which we have here. So, here we have our solenoid, and as you can see, the magnet is moving in. When the magnet is moving into the solenoid, the current is going to be induced to oppose that motion, right? So basically, you're trying to move the magnet in, and as a result of this changing magnetic field, remember, a changing magnetic field generates EMF. A changing magnetic field induces our current. You are changing the magnetic field by moving this magnet, and as a result, the current is kind of refusing that, and it's generating its own magnetic field to oppose that. And as a result, it's going to generate a current with north in this direction so that it opposes your magnet. Now, the reason that this occurs, as I said before, is the law of conservation of energy. So think about this. If you moved your magnet into the solenoid, and it induced a current that that pulled your magnet in. So you're standing there next to the solenoid, you have your magnet, and your solenoid is like pulling the magnet in, right? This doesn't make sense. Think about why this scenario doesn't make sense. Pause the lecture for a second and have a think about it. It doesn't make sense because that energy has just been like newly created, right? There is being a current that's induced, and your magnet is being pulled in. There's no resistance you're facing. It doesn't make sense. What does make sense is if you are changing the magnetic field, there needs to be an opposition to that motion to generate energy to create the current. So if you're pushing the magnet in and you have to it's being opposed, so you have to push in really hard. You're putting all of this energy into pushing the magnet in, and all of that energy that you're putting in, your applied force, is giving the electrons the energy to move around the solenoid. So the reason that Lenz's law occurs is because of the law of conservation of energy, right? You need to put energy into generating that current. This again occurs in the other scenario where you're moving the magnet out of the coil. So imagine you have your magnet in the coil and now you're trying to pull it out. But the coil is like pulling it, trying to keep it in the center. So you're trying to pull it out, the coil is trying to keep it in the center. The reason for that is because you are changing the magnetic field, which is going to induce a current, and you are inducing a current around the coil. So if you didn't need to pull on the magnet and put energy into pulling the magnet, there wouldn't be any energy for the current to be induced. So, of course, you're pulling it out, which means that the current is going to generate a magnetic field strength that opposes that motion. Again, the current is being petty. It's saying, oh, you want to move that magnet? I don't think so. I'm going to create my own magnetic field that stops you from doing that. That's how I still think about it to this day. So because of that, the direction of the current between these two images is going to change because now it wants to keep the magnet in there. So now this end is going to be the south because the direction of the current has changed. And it's going to pull the magnet back in. Okay, so that is basically the overview of Lenz's law and how it applies. This law kind of, as I said, was really tricky for me to understand when I was in year 12, especially when you get into like the application questions, and you need to apply Lenz's law to a whole different number of scenarios. So yeah, I hope that explanation really helped because it took me literally months to fully understand that. I'm not gonna lie to you guys. So by considering both Faraday's law and Lenz's law, we can derive an equation for the EMF induced in a loop with changing flux. So remember, the EMF is induced because the flux changes, the magnetic field changes. The section here about the EMF being proportional to the change in flux over the change in time is of course from Faraday's law, and then the negative out the front is of course from Lenz's law, because Lenz's law tells us the direction of induced EMF and Faraday's law tells us about the magnitude of the induced EMF. Okay, getting on to mutual induction, and transformers. So this topic is pretty simple. We'll go over it kind of quickly. So a pulsing, alternating magnetic field can be induced by feeding a coil with an AC current. So this magnetic field will induce a current of the same frequency in adjacent coils. And as a result of this, if the number of coils differs, the voltage can be stepped up or down according to this formula. So recall the use of transformers is, of course, if you are transporting electricity across long distances, such as in power lines in rural areas, you need to have a high voltage because that will reduce the power loss. However, when you're actually using power or electricity in your home, you don't want that larger voltage. You only have like regular appliances. So what you want to do is you want to change the voltage. And how we do that is using our step up, step down method with our two coils. So if you have energy moving in this wire and then it is put through this coil here, and then if you have another coil here that has less turns, what's going to happen is the energy is going to travel along here, and then it is going to go through this coil here, and the movement of the charge through the coil is going to generate a magnetic field, which is thus going to impact this coil, generating a charge through this coil, which will then move off in this direction. So that's why that works. And of course, our voltage of our primary coil divided by the voltage of our secondary coil is going to be equal to the same ratio for the number of turns. So if the number of turns is different, that means that we can determine or change, step up or step down the voltage. We can do the same thing with the power. So we know that the power of the input and the power of the output always needs to be the same, because if it weren't, then we would have lost or generated energy, which doesn't adhere to the law of conservation of energy. Remember, power is given by VI, so that's why this equation exists. So the power in the primary coil is going to be equal to the power in the secondary coil. Okay, before we move on to special relativity, I just want to give you guys like a few really quick tips for studying electromagnetism. One thing I really want to emphasize is making sure that you practice complex questions for especially like electrostatics and electromagnetism, like with like magnetic fields and the current carrying wires and moving point particles and solenoids. And the reason for this is because there's always going to be a really complex question of these on an exam. And you really need to understand the interaction of multiple different components. So for electrostatics, you're going to need to understand the interaction of 3 or 4 particles and how they impact one another, how their electric fields impact one another. You're going to need to do like vector analysis involving trig. So make sure that you practice those. And then for your electromagnetism, make sure that you practice questions that involve a lot of different elements. So that could be a current carrying wire, a moving point particle, a solenoid. Make sure that it includes Lenz's law, Faraday's law, all that kind of stuff. Make sure that it involves the right hand rule, this rule here, the FBI rule. Make sure that you practice combining all of the components together. Because speaking from experience, the reason that I lost marks on my physics external was because I didn't get one of the difficult magnetism question. I think I only got half marks. So yes, that is what really bugs me. And I practiced a lot of these questions. So that's my tips. Okay,